What we are going to discuss in the next 20 minutes, more or less, is about some of the results that are ongoing about the project, mainly focused on the world of mycotoxins. And in particular, as already explained by my previous colleagues, you can see that the architecture of the FoodSafeR project is related mainly to two main pillars, the microbial one and the chemical one, and substantially in the chemical hazards, we were working particularly with these different things. A first part, if we start from the end, is really related to, not exclusively, but mostly related to spices and herbs, where we are studying the illegal addition of toxic chemicals as a case study, in particular focusing in this moment on turmeric lead chromate case and other kind of potential adulteration from the chemical point of view with respect to the world, let's say, of illegal addition in the spices world. A second aspect is the one that was mentioned correctly by Panos, which is related to the study of the furans and other mycotoxins from the perspective of the, let's say, processing. So what we are trying to demonstrate is the potentialities of a combined analytical and statistical approach with pilot plants in order to mimic properly, close to the industrial processing, the different steps of the production to understand the evolution and the fate of processing contaminants like the furans, in this case in the food sources processing, and we are also studying some bakery processing like crackers or gluten-free pasta as meal solution process in order to understand evolution of specific categories of mycotoxins. Apart these two case studies, the part that we are discussing today as examples in the FoodSafeR project is this one in red. So we are now entering into aspects of these three different tasks about the prediction tools on the mycotoxins evolution depending on the harvesting condition year by year due to the climate change, and also together with this kind of prediction, having a monitoring of all the different kind of metabolites that are correlated to this kind of evolution, harvesting year by year, together with the development of innovative diagnostic tools for targeting in a quick and effective way some categories of emerging mycotoxins. In the present example, we are going to discuss the aspect of tropane alkaloids. So let's start entering into these three different cases. And okay, this is just a little bit of background, even if most of you for sure is already aware of the fact that in the present last decades in particular, we are experiencing the hard situation of, let's say, the change in, let's say, the climate effects, but also the different global resources that are changing the scenario about the development of these secondary metabolites of fungal growth in agricultural commodities that could affect the chain not only in the field but also during the storage, for instance, depending on the categories. And particularly when we consider different aspects about the environment, agronomical, storage practices, we need more and more, due to this stressor, the drivers that were presented in the start of this session, to predict and estimate the mycotoxins risk in advance, because this has big implications, for instance, for different players, different stakeholders in the chain, like the important aspect of risk management for decision-making to buy, let's say, in a specific region with respect to another, or optimizing the processing of the batches, the decision of where you have to drive a batch for food, for feed, for biofuels, etc., depending obviously on the prediction as well. A first activity of the project was dedicated to make a state-of-the-art of what was available in the scientific literature about the prediction modeling. And you have here some features of what have been tracked, and in particular, there is some information about the fact that most of the available literature is relying on grains, and there was only an example that was directly related to tomatoes in terms of predictions. At the same time, the top 5 most used input variables in this kind of prediction tools available in literature are related to, obviously, temperature and humidity, firstly, and then some rainfall and location as well. But the most important thing is the fact that there is more and more interest, as you can imagine, to integrate information that is coming from both environmental and agronomic inputs, and desirable also to have not general location, but potentialities about satellite geolocalization of the different sites to which the prediction should be then referred. Most of the toxins that are addressed in literature are obviously the well-regulated ones, like deoxynivalenol, for instance. And what is going to happen in the project, and this is really work in progress, is that we are trying also to address emerging categories of toxins like the Alternaria group, ergot, eniatins, beovericin, and we are trying to cover different grains categories from wheat to barley, rye, or maize, covering a set of years of harvesting campaigns, and in reality we are also going then to integrate also the 2024 as well. This is in progress. Trying to evaluate the potentialities of different models for the prediction, from, let's say, the more classical one to the more, let's say, evolved machine learning approaches, and assessing the best predictive models depending also on the combination of toxin category and corresponding grain commodity. So this is something that is still in progress at the moment, and probably next year we will have an overview of the result of this kind of effort. In parallel, as I mentioned to you, there's the interest of monitoring the pattern of different metabolites and mycotoxins that are evolving year by year, and in this sense, the reason, not only, but one of the reasons is the one that I mentioned to you, and this is a clear example. We have clear data about the fact that a couple of degrees with respect to the pre-industrial levels of increased temperature in terms of, let's say, climate impact is something that is really affecting a lot also the mycotoxin scenario at global, but in particular if we are focusing on Europe, and the fact that it's completely changing the, let's say, shift of the impact of some fusarium species in different regions of Europe, and also, for instance, the effect of aspergillus and aflatoxin contamination is completely changing and evolving with respect to what happened a few decades ago. So this is just one of the reasons for which it's important, the prediction, but at the same time to monitor and evaluate how the occurrence and the co-occurrence of the different species and metabolites is changing. And what we started to do from the first year of the project, so the 2023, the first, let's say, complete harvesting year, was to collect samples from different regions in Europe, and we did the same also in the last harvesting year campaign, 2024, and 2025 is just starting now, so we are starting also this third consecutive year of collection. And up to now we have about more than 200 samples of durum wheat from the different geographies, and about more than 100 samples of common wheat. And in this case, we were able to refer the different samples to, let's say, storage centers. This means that we cover a location of, let's say, a few kilometers around a specific storage center. And in a different situation, we are doing the same for the tomatoes, but important to say, in combination with the previous sentence, that in this case we are in condition also to geolocalize really the single tomato field. So in this case, we are collecting several consecutive harvesting campaign years with the contemporaneous information of the satellite geolocalization of each single field, and also evaluating different kind of agronomic rotation depending on the single fields with respect to use in the previous year of winter cereals, alpha grass, ryegrass, and having the possibility also to compare the different effect year by year. And also, I would add the fact that we are also combining organic and conventional agriculture in this kind of collection of these consecutive years. Up to now, we achieved about 100 samples, and another 60, 70 are coming from the present 2025 campaigns, which is just at the start in a month, more or less. What I can show you today is the result of the data elaboration of the collection of the first year of the harvesting campaign. We are now going to complete the data elaboration of the 2024 as well. But already from the first year, I can tell you that most of the grains that were analyzed contained alternaria metabolites, even if not high values, and particularly alternaria toxins were practically only the one really relevant in the tomato samples that were analyzed. At the same time, apart obviously the oxynivalenol and eniatins that were practically spread around all the different samples, some specific situation indicated the presence of T2 and other T2 metabolites in the different kind of samples in the different geographies. And this is what happened for the first year. Now we are going to have the second year overview, and we will proceed to have a comparison of the different years. What about the satellite? We are going to apply the satellite to the tomato cases, but we started already with some other preliminary studies. Here you have an example of what we tried to do with historical data coming from the Netherlands in order to evaluate the differentiation between the deoxynivalenol contamination in some fields in the Netherlands, exploiting information coming from historical data to compare the, let's say, prediction with respect to satellite vegetation indexes. More recently, we took about 80 samples from different fields geolocalized in Serbia for what concerned maize, and we tried to apply satellite vegetation indexes with respect to the geolocalization in order to generate a prediction of the different level of contamination of the fields and trying to correlate this information of the satellite data with respect to the level of contamination in the fields. And it was possible to generate this kind of binary classification about, let's say, high or low level of contamination with respect to aflatoxins and fumionizin. And this is something that was considered quite successful, and these reasons drive us to go for a further campaign from the same region in order to validate these results at the end of 2025. Finally, the last example about, let's say, the diagnostic tools. We are going to consider the category of tropane alkaloids. Well, the background here is that this is a typical situation related to invasive plants that can grow, let's say, in between other crops like cereals or soy, and this cross-contamination determines the production of secondary metabolites, like typically in the case, for instance, of buckwheat or corn, can be related to tropane, and in particular to atropine and scopolamine as the main toxins that could be present due to this kind of cross-contamination. And at present, the availability of methods for monitoring them is not always, but mostly related to a CMS analysis, so anyway, quite expensive and skill required kind of technique, while there is the need in the chain to have something more quick, rapid, and effective to be applied. And the project in this sense started to develop a specific indirect competitive lateral flow immunoassay for tropane, and in particular we started with the atropine molecule, and the assay has been developed, and it is very sensitive, and practically is based on innovative technique that permit to extract and concentrate in a paper strip the alkaloids and then dissolve them in the lateral flow strip device, having an handheld portable reader that permit to have a final semi-quantitative information about the concentration of the toxin. And we validated the kit in real conditions, also exploiting people that were typically lab operator, lab technicians, but also people that are completely not aware of any kind of laboratory good practices. So operator and people with no, let's say, skills from the laboratory point of view. And we tried also to compare the applicability of the kit depending on the different category of, let's say, population. And this exercise was successful, and we achieved the result that the kit is really applicable from, let's say, everybody. The cost is quite low because, as you see, it's practically a 3D printed system in which you have just the extraction tube, the lateral flow device, the, let's say, paper strip, and a very cheap RFID card reader. And we demonstrated the applicability in real conditions for atropine and scopolamine, and we are now trying to expand and take the prototype to the final commercialization level. With this, I would like to finish these case studies from the chemical side of FoodSafeR presentation, just making an acknowledgement to all these guys that were collaborating in the different goals that I show you, and I'm aware together with the colleagues for any questions from your side. Thanks.